Hi everyone, welcome back to another video. It's a somewhat tutor, and in this video we're going to be looking at working the total resistance for our circuits with series and parallel resistors. So hopefully by the end of this session you should be able to work out a lot of the complex circuits that you'll see in your textbooks. So let's look at this first example here. We've got a circuit with 4 resistors, 9 ohms, 6 ohms, 3 ohms and 3 ohms. So I've also attached a key at the top of the page. So we've got for series circuits we add the resistance, for parallel circuits we take the reciprocal, and then we finally take the reciprocal again to work out the equivalent resistance. So in this case what I'm going to do is break down how we work this out, how we go about working out the total resistance RT. In this case what I'm going to begin with is just assuming the current's flowing clockwise, and that's, it could be anti-clockwise, it could be clockwise. In this case let's just assume clockwise. So let's say the current begins at this battery. So at this point the current or the electrons are going to flow clockwise. What happens is as they come to this node here or this branch point, the current's going to split. Why? Because this branch and this branch are in parallel, they are not in series. So as you come to this node here, the current is going to split. Remember, in parallel the current splits. So the current can either go straight ahead or it can go down. Think about this as if you're driving a car and there's 2 paths to get to the same direction. You can either go straight or you can turn, and that's what the current's going to do. As the current turns, so let's say the current begins to flow towards this 6 ohms. This 6 ohms is now in parallel with these 2 resistors. If you imagine the current flowing at this point, if the current flows around this way, there's only one direction for the current to flow, which is clockwise in this direction. And then the current here again will meet up at this node. So the current from the 6 ohms resistor and the current through these 2 3 ohm resistors will meet at this point again. And as you travel through the final branch back to the battery, you should have your total current back. So let's break that down a little more. What we've established is at this point we've got a current split. Okay, so this branch and this branch are in series, parallel. Right, we've established that, but let's try and simplify this diagram by redrawing it. Let's work from the right hand side to the left hand side. We know this is one loop. This is a closed loop, so the current flows from that point down and around. So we know this circuit or this loop is series. So this 3 ohms and this 3 ohms are in series. So we can redraw this by using the first equation, R1 plus R2. So we got 2 resistors, 3 ohms plus 3 ohms. That is going to be 6 ohms as that's in series. So let's redraw that circuit. We've got our 9 ohm resistor, and then as we go down we've got 6 ohms. That's going to be one loop, and then we've got our series circuit of the 3 ohms plus 3 ohms, which is going to be 6 ohms. So that's going to be 6 ohms, and this is going to be our original 9 ohms, and that's going to be our 6 ohms. So we've established these 2 are in series. Now remember at the start we said this branch and this branch are in parallel, so that means the 6 ohms and this 6 ohms is again in parallel. So remember the laws when dealing with parallel circuits. We take the reciprocal of one of each, so we can say that 1 over RT is equal to 1 over 6 plus 1 over 6, and as we get the reciprocal of that, which is going to be 1 over 3, 1 over 1 over RT is going to be 1 over the third, which is 3 ohms. So what we can say is this 6 ohms, which is in parallel with this 6 ohms, is now equivalent to 3 ohms. So we can replace, or we can redraw the circuit as something like this. That's your 9 ohms. That's going to be our new 3 ohms. And then we've got our battery. So now, as the current flows, in this case again, we're going to assume clockwise, there's no node with a breakpoint. It's just going to be one loop. So we can say the 9 ohms and the 3 ohms is in series. Remember, if we look at this diagram, it was the same. At this point, the current again just splits. So therefore, the 6 ohms is in parallel with the 6 ohms. So in this case, the simplified diagram, RT will just be 9 plus 3, which is equal to 12 ohms. And in this case, we've also got our total voltage as 12 volts from the diagram here. Therefore, we can say that the current in the circuit IT, the total current is 12 volts divided by 12 ohms, which is equal to 1 amp. So hopefully that's made sense. If not, let's try another example. So welcome back to another example. In this case, we've got another branch added within our existing circuit. So let's begin at the battery, at the power source. Let's assume the current flow. We're going to assume in clockwise direction, so we've got current going up. We're going to turn at this 15 ohms. Now we've noticed there's a branch, so the current can either flow downwards or it can carry straight ahead. So what does that mean? It means this branch and then this entire loop is in parallel. Okay, so we've established there are two sets of loops and they are in parallel with each other. Right, let's carry on at this 4 ohms. As the current travels, it goes down and then there's another node. So the current can either go to the left or to the right. So what does that mean? It means that these two resistors are now in parallel. And at this point, once the current will drop down and enter the node here, and then enter the node here. So the current at this node must equal this node. So the current comes back down and then goes back to this node here, and then at this node the current will draw back from the 10 ohms, and that should be the total back here. So let's break this down. As I like to do, I like to work from the right hand side back to the left hand side. What I'm going to do is just clean up the screen. So let's work with this loop first. So we established the current splits at this point and then regains at this point. So the 12 ohms and the 12 ohms are in parallel. So we use the parallel law, which is the reciprocal of the resistors, which is 1 over 12 plus 1 over 12 is equal to 1, 6. And that's going to be your R reciprocal of your RT. So therefore, RT is equal to the reciprocal of 1, 6, which is 6 ohms. So if we draw that circuit, what does it look like? We've got our battery, our 15 ohms, we've got our 10 ohms here, we've got our 4 ohms, and now the newly formed 6 ohms. Now, can you see where this is leading? Exactly like the previous example. So, as the current, if we look at, this is the first loop, so let's just say this is the first loop, and then the second loop. If we focus on the second loop, as the current from this point travels only in one loop, these two resistors must be in series. So what is that? This happens to be 6 ohms that we just worked out, and then this is your 4 ohms. So therefore we can say the combination of these two resistors, which is 6 ohms plus 4 ohms, is equal to 10 ohms. That's in series. So how does the circuit now look if we clean it up? So we've got our 10 ohms, that goes down, sorry, that's our 15 ohms, down to our 10 ohms, That's the first loop. Now, we've just established that those two resistors, 4 ohms and 6 ohms, are in series, as there's only one way for the current to flow. So that becomes one total resistor of 10 ohms. That's 10 ohms, and that's 15 ohms. Now, remember at the start, we assumed the current direction to be this way, clockwise. At this node, the current splits. Either it carries on going straight, or it goes down to the 10 ohms. So what does that mean? It means that this branch with the 10 ohms is in parallel to this loop. So this 10 ohm resistor is in parallel to this 10 ohm resistor. Now that means if we take the equivalent resistance, which is the reciprocal of each resistor, that equals 1/5, and then we can say RT is therefore 5 ohms. So if we clean the circuit up, what I'm going to do is just clean the screen up for a second, and we can visualize what the circuit looks like. So what does the circuit look like? So we've got our 15 ohms, our newly formed 5 ohms, that is 15 ohms, 5 ohms. We've also got a 30 ohm resistor which I've been forgetting about, so let's just add that in. So let's just say that's 30 ohms there. Again, as I've left it out, it's not been a big issue because it's all in series. This loop here, remember the current all regains back at this point, and this loop is always clockwise. As there's no current split here, it's not been an issue. So we can say that the total resistance is equal to each resistance added together because it's in series. So we use this law as stated. So that's 15 ohms plus 5 ohms plus 30 ohms. So we can say the total resistance is equal to 50 ohms. Therefore, using Kirchhoff's law, V equals IR, we can say that the total voltage divided by the total resistance is equal to IT. So that equals to, so we've got 12 volts here, divided by 50 ohms. So therefore, IT is equal to 0.24 amps. So hopefully that's made sense. If you've enjoyed the video, please leave a like, please consider subscribing, and if there's anything else you'd like to know, please leave it down in the comments.